I'll just start by giving you sort of just like a brief, context. As you know from this class, probably that, understanding how the brain works is among the most complex and challenging issues in science today. Former President Obama famously called this the century of the brain. Is going to be now the century where we finally sort of understood how the brain works and functions and things like that. And so there's been a fair amount of sort of resources put towards the goal of better understanding sort of how the brain works and how it affects our health and whatnot. And so in general, when we talk about neuroimaging, it's sort of a umbrella term for a large number of a family of different sort of minimally invasive techniques designed to study the brain. And this could be sort of studying brain structure or brain function or sort of disease pathophysiology. And so in general, we often sort of separate neuroimaging into two basic categories, either structural neuroimaging or functional neuroimaging. And so when we talk about structural neuroimaging, it's usually we have a single snapshot of the brain, and so, we can use this to sort of study the brain structure and diagnose disease or injury. So, for example, if you've been in an accident or you believe that a doctor believes you've had a stroke, you might get a structural image, and then you could look for sort of damage or irregularities in the brain. And so these types of images have a very high spatial resolution, but no inherent sort of temporal resolution. It's sort of like a snapshot of a single picture of your brain at a certain period of time. But they're very good at sort of distinguishing different tissue types in the brain and sort of seeing whether there's any sort of irregularities or strokes or lesions in the brain or damage. Now, functional neuroimaging is a little bit different. It's almost like if structural neuroimaging is like a picture, functional neuroimaging is more like a movie, a series of pictures, rapidly taken in time. And so basically, we acquire a bunch of these images in time while people sort of either perform a task or simply rest or whatnot. And so in this case, we have a temporal resolution. It could be every second or something like that. But we usually have lower spatial resolution because we can't start acquiring the second image before we finish the first. So there's a little bit more of a time constraint in how much time we can spend on sort of getting each image. So typically they tend to be of lower spatial resolution, but we gain having a temporal resolution. And so often we try to relate changes in signal to some experimental task. Now we can talk about connectivity in both structural and functional neuroimaging. And structural neuroimaging, it's often using things like DWI to get sort of pathways between different brain regions, tracks between different brain regions to see how they're sort of connected. And that gives us sort of a map of connections in the brain. However, today I'm going to focus more on connectivity in the context of functional neuroimaging, and that's how different brain regions tend to activate or in relation to one another. And so my primary focus in the neuroimaging world is on fMRI, or functional magnetic resonance imaging. So this is one of sort of many ways of sort of non-invasively studying brain activation, but it's probably the most popular because of a number of reasons. One is that it's readily available at most sort of hospital or research institutions. The same scanner can be used both for clinical and research purposes. It's relatively cost efficient, and in particular compared to some other things like PET, and also there's no known sort of side effects of it. So, for example, a PET scan, you have to ingest a sort of a radioactive chemical, so you can't do that every day. But a MRI, you could basically get every day without any known sort of side effects. And so therefore, they're very useful for things like longitudinal analysis where you have to scan people repeatedly and whatnot. So it's sort of become the most popular technique. But let's sort of focus a little bit on what the data looks like. What it looks like is that you have a sort of a brain volume, and you sort of think about splitting this brain volume into about 100,000 different boxes. And so these are called voxels, volume elements. And so these are cubic volumes that span this sort of three-dimensional space. And so this is sort of the unit of measure that we have in fMRI. And so each of these boxes have basically two pieces of information. One is they have a location, where they are. They're in the visual cortex, in the amygdala, they're wherever, they're the frontal cortex. They also have an intensity value. And so the intensity value is what gives us the image. These grayscale images are just pictorial representation of these intensity values that we have in these, maybe 100,000 or so voxels. So in an fMRI experiment, we might acquire several hundred of these, maybe every second or so. It can range from maybe 500 milliseconds to 2 seconds are standard studies. So that's a temporal resolution. And so basically now we have repeats of this across time. And so remember those two pieces of information. One was the location, which is constant across time, hopefully. And the other is the intensity, which can change over time. And so if we fix the location to be this sort of green voxel, and we extract the intensity in each of at this green voxel at each time point, then basically we get a time series, right? So we get one measurement corresponding to each of these time points in this particular spatial location. And now we can sort of do kind of time series analysis and the like. We can sort of correlate this with the task. So for example, here I have this little cartoon image. I have like an on-off task where you have off for 20 seconds, and then for 20 seconds you tap your fingers on and off. And then basically you see in this voxel, the intensity is going up when you're finger tapping, and it's going down when you're not finger tapping. So this would be a indication that this voxel is reacting to this task, and this is sort of task-related activation. Now you can do this at every location in the brain, and you can sort of figure out, which voxels are doing things and whatnot. And so this is basically what the analysis of fMRI data is. It's a time series problem, but it's a very big time series problem because you not only have a single time series, you have about 100,000 of these time series. And there's going to be a complicated correlation structure in time, but also in space between. So adjacent voxels will probably have spatially correlated noise and spatially correlated signal and things like that one has to take into consideration. And so the analysis of fMRI data is sort of a kind of a modern statistical big data problem. It's sort of like omics and other types of similar data structures. These are big data, and you have measurements from each subject consists of maybe tens of millions of different measurements, and subjects can be brought in repeatedly for longitudinal studies, and an experiment that can be repeated for multiple subjects. In smaller labs, it might be 10 subjects, but in the UK Biobank, for example, there's 100,000 subjects with imaging. So this is a sort of a super big data. There's a massive amount. But big data is itself not a problem. That's just the problem of sort of storage and computational resources. The thing that makes imaging hard is that it's also complex, right? So it's not only large, but has this complex correlation structure, space and time across subjects. So people that are in the sort of same familial group might have correlated signal. If you're seeing the same person over time, they'll have correlated signal, and so it becomes quite difficult to sort of analyze these types of data sets. So statistics, of course, plays an important role in sort of understanding these types of things and obtaining sort of relevant results that can be used and interpreted by neuroscientists. So it's a very cool problem statistically, and it's been a sort of a kind of a gift that keeps giving, in the sense that there's people enhance the modalities, increase. There's technological advances and advances in sort of experimental design and what you're doing while in the scanner, and that opens up sort of new statistical problems all the time, which is really exciting. So what are the sort of the primary things that we want to do with this data? one classic thing is, can we identify the areas of the brain that activate in response to a task? So in my little cartoon image, I said we finger tap for 20 seconds, we rested for 20 seconds. Which areas of the brain are active when I'm finger tapping? Well, you could basically look for sort of task-related signal, and you could do a hypothesis test at each of the 100,000 locations, and you can sort of color code the p-values, and these are basically brain activation. So these are sometimes some of these pictures that you see in journal articles where you have a brain with sort of color on top. These colors are actually the results of statistical tests. So these are p-values. Usually these are usually the colors. The blue ones are negative activations, and these are positive activations. And so what researchers often do is make brain maps like this, and use these to sort of figure out which areas are active. And so I usually refer to that as brain mapping. Now, the thing that we're going to be more focused on today is something different. Let's say that you have a couple of brain regions that are active. You also want to understand how they sort of communicate with each other. And so you want to understand, how do the brain regions interact, and say, how does this depend on experimental conditions or behavioral measures? Does the interaction between two brain regions change if you change your brain state, or is it different for people with certain sort of behavioral outcomes? And so here's one example of regions in the brain that are sort of spatially that are correlated with whose time series are correlated with each other. And this is kind of a famous example. This is something called the default mode network, where that there's a time series here in this PCC here, and it's very sort of highly correlated with areas in other regions of the brain, but it's also sort of negatively correlated with other regions here. Here's another example, just showing kind of what kind of looks like almost like a social network of types superimposed on the brain, and that's sort of a very standard type of thing as well. And this is an important type of thing, because you're trying to understand which regions are sort of important, which regions are hubs in these types of networks, and how does information flow through the brain in this manner. And here's a third example, showing more directed influences between different regions. The third and final thing that people often use this type of data for is for prediction and classification. Can you use a sort of a person's brain activation or their structure to predict something about them? Can you look at a person's brain activation and say, is this person in pain? Does this person have schizophrenia, or is this person at risk for Alzheimer's disease? Those are the type of things that people are sort of interested in, and this becomes sort of a machine learning problem. And here you can imagine putting in brain activation to some prediction model or classifier, and then getting some output. And so this is an example of a pain predictor that we've developed, where you basically put in brain activation, and these are sort of the coefficients corresponding to each of these. So if you have a lot of activation in these regions, you predict more pain. In these blue regions, if you have a lot of activation there, it sort of suppresses your pain report, and that gives that. So these are all sort of areas that there's sort of active research interest in. But today I want to sort of focus on the second one, which is this brain connectivity. And there's sort of different types of brain connectivity. And so I think, like, fMRI was sort of developed in the early 1990s. So it's about 30 years old about this time. And so I think the first 15 or so years, people did mostly these brain mapping studies. But then in the early 2000s, people started moving over to doing brain connectivity studies. And there's a couple of reasons for that. Which I'll mention. And so the idea here is of trying to sort of understand how different brain regions interact with each other, and how this sort of interaction sort of depends on either experimental conditions or behavioral measures. And it's really become very common to talk about brain networks. And so these could be sort of sets of interconnected brain regions that don't have to be sort of spatially adjacent to each other, with some information transfer among the regions. And so how do you construct a brain network? Well, one way would be that you just define a set of nodes. These are sometimes called regions of interest or parcels of the brain. So you might split the brain into different things. In this little cartoon, I just split the brain into three different nodes. And then I might look at the edges between these nodes. And these edges could either be bidirectional or directional, depending on what type of analysis I'm doing. And these can also, of course, be represented as a matrix, where it's the one element of this matrix is the connection with A with itself. This is the connection with A and B. This is a connection between C and B, for example. And sometimes they're also given by adjacency matrices, which are basically just a connection matrices thresholded at 0 if they're 0 and 1 if they're non-zero. And so these are a number of different ways that we can sort of represent connections between these three brain regions. Here's a pictorial, and there's different ways of doing this. And so at some level, often it's a goal to sort of get these types of things, and then see whether or not there's some difference between different groups of individuals, or whether this changes as a function of time or other things. One of the, I said that there's been an explosion of interest in connectivity in the last 15 years. A lot of this has been driven by something called resting state functional MRI. And so in the early days of fMRI, when people were doing these brain mapping studies, we often did what's called task-based fMRI. So you had people perform a task while they were in the scanner. It could be that they were finger tapping and resting, or they were viewing something, or they were doing some psychological experiment, Stroop task. The different, they were gambling. Like there was different things that they could be doing while they're in the scanner, and the analysis was always about sort of figuring out which areas of the brain were activated when you were performing that particular task. But some 20 years ago, it was sort of found that, of course, the brain is always active, even in the absence of an explicit task. And so even if you're not performing a task, your brain is working in some way. And so people got very interested in sort of scanning what people looked like while they were resting. And it turned out that there was a lot of sort of synchronous bold changes, so changes in signal between multiple brain regions while the subjects were in the scanner but didn't perform an explicit task. And this was very consistent across subjects in multiple sessions and across different subjects as well. It was very consistent that the same sort of brain regions were communicating with each other while these people were just sitting in the scanner, right? And so this was very promising, because there's a number of reasons why this became very useful. One is that scanning, if you can scan people while they're performing a task and get a certain information, and if you can get sort of equivalent information while scanning them while they're doing nothing, that's almost preferable, because that takes away the sort of the burden on the patient. So that allows you to be able to scan people that can't follow the instructions for whatever reasons. They might be too sick, or they might not understand the instructions. And another thing that it allows you to do is to more easily share data across different sites, because it's hard to align to make the same task at different sites at different labs. But resting state data, it's easier to make it equivalent across different groups, and because they're basically all resting in the scan. So what happened is that a lot of people could then sort of share this resting state data, and then suddenly we had these data sets that were in the thousands, because people were sharing their data. And there were things like the 1,000 functional connectomes and things like that. So this suddenly allowed us to do a lot more types of analysis. But of course, whenever you're doing this, the signal's a little bit weaker. It also sort of changed the paradigm of statistics in neuroimaging, because previously a lot of the analysis was about finding sort of correlates between the task and the signal in the brain, and making those brain maps, color coding sort of which areas were active or not. But that sort of doesn't really work in resting state fMRI, because we don't know what the subject is thinking about, so we can't sort of correlate it with anything. So instead, what you have to do is you have to correlate different brain regions with each other, and so that sort of gave rise to this explosion in sort of connectomics, where you sort of want to try to understand how different brain regions are going up and down in tandem with each other. And so that's driven a lot by this resting state fMRI, because there's nowhere, this is sort of the only way you can really analyze it, because there's no task that you can sort of anchor it to. So that developed this need for alternative strategies, and so that led to sort of this explosion in connectivity analysis. And so in general, when we talk about connectivity in the brain, we generally talk about two different types. One is called functional connectivity, and the other is called affective connectivity. And so functional connectivity is defined as sort of the undirected association between two or more fMRI time series. And so this makes sort of statements about the structure of relationships among brain regions. It doesn't really make any assumptions about sort of the underlying biology. It's basically just a statement about correlation between two brain regions, how they sort of go up and down together. It doesn't say anything about why this is happening or not. But basically, you can make sort of statements that, oh, this brain region is correlated with these three different brain regions. And that would be a sort of a functional connectivity study. Now, affective connectivity is a much more ambitious thing. Here you're trying to make sort of directed influences on one brain region on another brain region. And so usually these are sort of anatomically motivated assumption, and restricts inference to sort of networks comprising of a number of pre-selected regions of interest. And the goal is to make sort of causal claims about how tasks and regions are related. So V1 gives rise to activation in V5, which gives rise to activation in PPC. And so this is much more ambitious, right? Because in functional connectivity, we're interested in sort of correlational things. In affective, we're interested in more causal things. In general, I don't think people have sort of completely understand causal inference in the neuroscientists. So sometimes the boundary between affective connectivity and functional connectivity is very blurred, and very rarely are we able to really get at causal effects. But I just sort of want to mention this for sort of completeness. So how do you do this type of connectivity? Well, there's lots of different ways of doing it. I think that sort of, when talking about functional connectivity, sort of the three most sort of popular ways of doing it are probably the following. One is to sort of just choose a seed region and look at its correlation, the correlation between activation in that region and every other region in the brain. There are sort of inverse covariance matrices methods, which have been popular in statistics for the last decade or so. About finding sort of the link between sort of zeros in a precision matrix and the existence of an edge, yes or no. And so we'll talk a little about this. But I think the primary thing has been these sort of multivariate decomposition methods, and in particular a technique called independent components analysis has found sort of widespread use in the fMRI literature. So let me just talk briefly about these things. So the seed analysis is probably the simplest thing that you could do. You're saying, well, hey, let me look let me extract data from the amygdala. As an example, and I get a time series from the amygdala, and now I want to calculate the correlation between that time series and every other voxel of the brain. So that therefore you're going to get a correlation value for each location in the brain, and you're going to get sort of hotspots where for the regions that are highly correlated with the brain. And so this allows, researchers to find areas that are highly correlated with activation in the seed region. And so this is the example that I already showed you. This is a paper from Fox et al. From 2005. And this is kind of a famous paper because what they did is they took a seed here and they found that in certain regions of the brain, it was really highly correlated with it. And so even far apart from each other. But in other parts of the brain, if I took this seed in these blue regions, was actually what they would call anti-correlated or negatively correlated with it almost perfectly, right? And so this is something that has come to be named the default mode network, and this is very consistent across subjects. So if I scan any of you in the scanner while you're doing nothing, your brain is basically going to behave in this manner. These regions are going to be sort of highly correlated, and these will be highly anti-correlated. And so this is a very sort of well reproducible pattern in the brain, and so that created a lot of sort of interest in sort of studying these, and so this is an example of a brain of what we would call a resting state network, and I'll return to this later. So there's a number of sort of very clear network patterns that are sort of extractable when a person's at rest, and so this is the first example. Sort of the inverse covariance methods, it's sort of based on this sort of kind of a cool result that if you're working with sort of multivariate Gaussian data, there's a relationship between the inverse covariance matrix, or the precision matrix, and the graph that represents relationship between the regions. And so you can make these sort of conditional independence graphs using things like graphical lasso or things like that, and use this to sort of estimate sparse precision matrices and graphs. So the idea would be that if you got a precision matrix, so the inverse of the covariance matrix, and you have zeros in certain locations, that's indicative that the edge between, say, A and C here is a zero, right? And so there's a sort of one-to-one mapping for multivariate Gaussians between zeros in this inverse precision matrix and the graphical structure. And so this is a nice way to sort of create these graph networks. Of course, it depends a lot on you get these zeros by adding penalization terms and so it depends a little bit on those types of things. But this is sort of showing some of the differences between these. If we just do standard correlations between different brain regions, you're going to get a lot of sort of almost everything is going to be connected in some way, because if this guy and this guy is correlated and this guy and this guy is correlated, then presumably those two regions will also show a correlation. But if you do a partial correlation between them, you tend to get a sparser and more interpretable graph. So a lot of these areas that have been sort of hot in statistics about finding these sort of conditional independence graphs become very, very, very important here as well, as they give very sparse and interpretable graphs. So that's a sort of a second way of finding these things. I think the most common, though, has been using sort of decomposition methods. And so there's a lot of different, the one that's sort of most familiar, sort of to statisticians at least, is to perform principal components analysis. But so independent components analysis is a sort of a cousin, I guess, but it's a family of techniques used to sort of extract independent signal from the same source signal. And so ICA allows us to sort of blindly separate the data into sort of spatially independent components. And the key assumption here is that the data set consists of p spatially independent components that are sort of linearly mixed and spatially fixed. And so what do I mean by that? Well, I think the classic way of sort of understanding ICA comes from this sort of cocktail party problem. And so imagine that you're at a cocktail party, and there's two conversations going on. One conversation is going on over here, and one conversation's going on over here, right? You also have two microphones in the room, here and here. And so this microphone here is picking up some of this conversation and some of this conversation. So it's a mixture of these two conversations. Now, this microphone is also picking up a mixture of it, but it's a slightly different mixture because the mixture depends on if this microphone is really close to this person, it's going to be dominated by this conversation and pick up very little of this. While on the other hand, if this one is closer to this, the opposite will be true. And so here we have two speakers, S1 and S2, which are speaking over time. And we have two microphones, which are picking up some sort of combination of these two over time. And so we can write the microphone data as follows, that microphone 1 at time t is picking up conversation 1 with a certain weighting and conversation 2 with a certain weighting in some linear combination. And the same is true of microphone 2. It's picking up some weighting of these two conversations. Now, this is what do we know here? Well, in this case, we know what X1 and X2 is because we have the recordings, right? We don't know what S1 and S2 is, which are the conversations. And so our goal is, can we use these recordings and extract what the two separate conversations was? And so this is the cocktail party problem. And so in general, if you know what these A11, A12, A21, A22 are, then this is sort of a rather trivial problem. You just have that X is equal to A times S. And if you know X and you know A, you can solve for S. It's two equations, two unknowns. It's not a big deal, right? And so, but in general, in ICA, we want to solve this problem knowing just X. So we don't know what S is, and we don't know what A is, right? And so that's now it becomes from a trivial problem to an impossible problem, right? I mean, we now have two equations and we have six unknowns, right? That doesn't seem doable unless you put some sort of assumptions on the problem. And that's what we need to do in ICA, right? And so this is sort of the ICA model. A is called the mixing matrices, so it's sort of mixing these conversations, and S is the source matrix. These are these underlying conversations, and our goal is to find some way of unmixing W such that this unmixing gives us a good approximation to S. And so this is at its core what ICA is all about. Again, if the mixing matrix is known, trivial. However, ICA solves this problem without knowing any of the mixing parameters, and that's a terribly difficult problem now. And so what you have to do is you have to put a lot of assumptions on the problem. One is that there's a linear mixing of sources. The components SI have to be statistically independent. And actually, the components SI are non-Gaussian, or actually only one of these components can be Gaussian. And that's why you know that a statistician didn't think about this, because a statistician would never consider something to be non-Gaussian. So this is a sort of a very engineering way of doing this. And so independent component analysis is a way of sort of extracting this signal from some source matrix. And so this is basically, we can do this also in fMRI, in the sense that we have voxels by time. So this is the data. This is this four-dimensional data set, this three-dimensional brain volume across time. But if we string out space in one direction and time in one direction and do an ICA decomposition, then basically what we're going to do is we're going to get spatially independent components, which correspond to sort of the speech patterns. And then the time series are going to be how these things are mixed to make the data. And so actually the techniques that work for this cocktail party problem work very well for fMRI as well. And we can use an ICA algorithm to find A and S. And the output are things like this. So we basically get spatially independent components with corresponding time series. And so this is sort of a way of breaking down the data into a number of different components. And then we can analyze them. And so here there's certain regions that are co-activating, and their co-activation pattern looks like this. And then we can sort of interpret that. Here's another bunch of regions that are co-activating. And this is sort of a classic type of thing because it's sort of like a ring around your head. And like it's almost like a helmet around this person. And that's usually indicative of a nuisance thing, like motions, that you're bobbing your head a little bit, and that this voxel is going in and out of the brain. So it's giving rise to an artifact, and you're seeing this very coherently. So ICA is very good at finding these types of artifacts from the brain. And so using ICA, you can identify similar things. Remember, I called this a default mode network. Here's another example of the default mode network extracted using ICA. And here are some other sort of components that correspond to sort of resting state networks that are consistently present in people and that we often find and want to analyze. I think I'm only going to briefly talk about effective connectivity, but these are sort of are methods that put a little more structure on the data. They tend to be a little bit more ambitious, but the question is whether they should be deemed ambitious or not, because they make a lot of sort of leaps of faith in trying to assess causality and stuff. But in general, some of the more popular methods are structural equation modeling, Granger causality, and something called dynamic causal modeling. You'll see the word causal comes into play a lot there because that's what people's end goal really is. So these techniques basically just you look at a bunch of you basically hypothesize a network like this. Here there's three different regions, and they have a unidirectional flow in this manner, and you want to basically sort of estimate using activation in these A, B, and C. You want to estimate what these paths are. You know, the strength of path between these, how this information transfer takes place. And so this is all sort of assumed a priori. It's often, I think, erroneously given a causal interpretation, but you can sort of set up a problem like this. If this is the brain activation in A, B, and C, this is just showing in a structural equation model how if you have activation in A, how does that give rise to activation in B? Well, activation in A gives rise to activation in B through this BAB parameter here, and then plus some noise. And so there's a number, and so this is the model here that people use, and so you can rewrite this in the following way, and then you can basically, this is sort of your theoretical covariance, and you can try to figure, you can compare it to sort of your empirical covariance to sort of estimate these model parameters. So again, to me, this is still sort of correlational in its structure. Just because you draw arrows between it, there's nothing sort of inherently sort of causal about this. You're not manipulating anything, but people sort of tend to make sort of stronger conclusions based on this. And so this is an example of what we would call effective connectivity, you know, over functional connectivity. It's usually that we're making sort of directional assumptions and on hypothesized models and trying to figure out whether this, we can also do model comparison. So for example, if you hypothesize that it looks like this, and I hypothesize that this BAC is equal to 0, we can sort of estimate both of these networks and use sort of models, comparison methods, AIC, BIC type stuff to sort of compare with which, or you could do some sort of Bayes factor type stuff to sort of compare different models. And so this is usually done when you have sort of a clear hypothesis of how, you know, it might be from animal models or from previous research, but you sort of have an a priori idea how things are connected. A lot of the functional connectivity is sort of more data driven, right? So ICA doesn't really care about prior research in the sense, or the seed analysis. It's just about which areas are have a correlation with each other. So again, you know, this is you know, in SEM you're trying to sort of minimize the difference between the observed covariance matrix and the one implied by the structure of the model, and this allows you to get these sort of modeling parameters. So I'm not going to go into detail, but that's basically the idea. dynamic causal model is something that's very related to this, but it's much more ambitious, actually. And basically, it tries to sort of do a two-level model. One, you have a neuronal model, a latent neuronal model that shows how different brain regions interact. And this is supplemented with what's called a forward model of how this neuronal activation is transformed into the observed responses. And so I'm going to make this little cartoon here that here we have two regions. I'm going to call them Z1 and Z2, and they're sort of communicating with each other in this way on a sort of neuronal latent level, which I'm not privy to. I can never see this, right? But what I can see is I can measure, and let's say that you have inputs. I do some input to this system where I manipulate Z1 and I modulate the connection between Z1 and Z2 somehow. How does that impact this system? Well, the only way I can do it is by measuring the hemodynamic thing, which is not the neuronal firing. This neuronal firing gives rise to sort of a hemodynamic response, which I can measure. So the goal of DCM is to look at these hemodynamic responses and through a number of modeling assumptions, sort of be able to figure out what was the neuronal firing that must have given rise to these hemodynamics. So this is a quite a difficult problem, and so you have to make a lot of different assumptions about how these things are connected and how neuronal firing gives rise to brain hemodynamics. And so it's quite non-trivial, but it's sort of an area of a lot of research. So again, I'm not so bullish on effective connectivity because I think that they make a lot of assumptions, but I just want to sort of cover them for you know, to make sure that, you know, just for so that you have the full gamut of techniques that are used. But if we go back to sort of functional connectivity, let's say that I do sort of a inverse covariance matrix method, and I get a connectivity matrix that looks like this. What can I really say about this? This is a mess, right? I mean, there's a lot of different connections here, but it's very hard to interpret these findings, right? So what people often want to do is sort of a secondary analysis, looking at this type of thing and trying to see, are there some properties of this network that is sort of predictive of sort of health status or whatnot. And so it's become really popular to use sort of graph theoretical approaches to investigate sort of the organizational principles of the brain. And so there's things like small worldness, modularity, the existence of highly connected network hubs, that's become very important. So there's now a secondary analysis of these networks to sort of better understand things. And this is pretty important because it can tell you a lot about sort of clinical things, because let's say that you have a hub, and a hub is where every brain is like like when you're flying, right? If you're flying Delta, the hub is Atlanta, so every flight has to go through Atlanta, right? But to Baltimore, it's not a hub, so very few flights go through Baltimore, right? And so, in general, if they shut down Baltimore Airport, Delta isn't influenced that much, right? But if they shut down Atlanta, there's chaos, right? And Delta, because no planes can get anywhere because everything has to go through Atlanta. And the same thing is true in the brain, right? So there's certain brain regions that act as hubs that all the other brain regions are sort of communicating with it, and it's sort of dispatching information. So if you have a stroke there or you have brain damage there, then that can have very dire consequences because the brain can't compensate for that. However, if you have a stroke in another brain region that's not a hub, it might be that the brain has different ways of compensating for that and moving information. And so this has become very important for studying these types of things. And so you can also look at how these different networks communicate between different sort of disease groups and see if whether, you know, say schizophrenics have a different network status than non-schizophrenics. And so there's a number of things that we can do. And so basically, if a network looks like this, we can calculate things like we talked about the adjacency matrix as which regions are connected to each other. We can do things called clustering coefficient. And if you have a high value on the clustering coefficient, that means like, for example, here, C has a very high clustering coefficient. That means that if you leave C, the chances are that you're going to be able to get back to C because you're in a kind of a cluster. Now, B has a very low one, right? Because if you leave B, then you might wander off here and never return to B because he's a little bit there. And then there's things like path lengths. How quick can you get from D to B? Well, you can get to it in two jumps, right? And the quicker you can get from here to here, the more efficient sort of brain organization is. And so those are things that people look at. And so here's a little bit of a cartoon a postdoc of mine put together showing different sort of local graph properties and global graph properties over the whole brain. These are things like small worldness and things like that. And then so in between these meso level things. And so it turns out that you know the brain is sort of has this sort of small world structure where you have adjacent regions are very highly connected, and then they have long range connections that allow you to sort of jump between the brain. And so those are sort of things that people are quite interested in as a sort of secondary analysis of some of these networks. And so the final thing that I just wanted to talk about is something called dynamic or time varying connectivity. And this is sort of an interesting thing because imagine what I'm asking you to do. Like, let's say that we have resting state data and I say, be in the scanner for 10 minutes and do nothing. Of course, it's impossible to do nothing. And so it could be that in the beginning, you're thinking about, oh, this is very uncomfortable. Why did I agree to be in this study? I wish I was at home. Then you might say, okay, this isn't so bad, but I have a lot of work to do. And you might be thinking about some of your work. And then you might be saying, oh, when I go home, I have to buy some milk on the way home. Or, your brain is wandering. So chances are that as your brain is wandering like that, different brain regions are communicating with each other. And so the idea behind, so a lot of the methods that we talked about before is assumed that the correlation between this brain region and this brain regions are sort of constant across the whole sort of 10 minutes you're in the scanner. But a lot of studies have shown that that's not the case, that maybe these two brain regions are communicating for 1 minute, and then later on this brain region is communicating with a different brain region. And so that's led to this sort of dynamic connectivity where you try to look for changes in brain activation over time. And so this is sort of interesting to study because it stands to reason that maybe some groups of people, you can imagine that maybe say children with ADHD whose mind wander more, they might switch states more commonly than sort of typically developing children or something like that. And that's the type of sort of inferences that you seek to make. And so here's a few methods for doing that. You can do sort of a change point analysis on sort of these connectivity things and say, well, oh, there's a change point here, and before that change point, the graph looks like this, and after it looks like that. Other people have done, things like there's one that's commonly used as sliding windows, is that they just do a sliding window and they calculate the correlation in each sliding window over time, and then they cluster these into different brain states. So that's another way of doing it. You can do things like hidden Markov models and the likes are all sort of popular techniques. In general, there's sort of two different paths towards doing this. You both start in both paths, you start with sort of a multivariate time series data, and then you do something like sliding windows to estimate sort of time varying connectivity matrices, and then you cluster them with something like k-means to get these sort of brain states. And sort of the second approach would be sort of to do something like hidden Markov model or these change points to take this multivariate data and sort of separate the time course into different segments where you have different sort of network structure in different segments. And so those are sort of things that you want to do. And then you can look at sort of some secondary data analysis. How long do do you stay in a state? How long do you how often do you switch states? And is that related to something about you as a person, or to your disease status, or things like that? So that's a sort of a become increasingly common thing to do more recently. So that's sort of, I think I'm running sort of short on time here, but that's basically, I just wanted to give you an overview of sort of the functional connectivity and affective connectivity world, talk about some of the methods that people use, and then, and talk about some of those things. And so again, as mentioned, I have a Coursera class, or it's on YouTube as well, if you're sort of interested in that. Thanks.